Hi folks, in this video we are going to see the derivatives of trigonometric functions. We are going to start with some special trigonometric limits, and we're going to see how we can use those limits to evaluate the derivative of sine and cosine, and then we're going to see the other trigonometric, the derivatives of the other trigonometric functions at the end. So like I said, to determine the derivatives of sine and cosine, we are going to need to use two special limits. So the first one says the limit as x goes to 0 of sine of x over x is equal to 1. And the second one is the limit of cosine of x minus 1 over x as x goes to 0, and that is equal to 0. So let's see the first special trigonometric limit. So we make an observation that for x near 0, the function sine of x over x, it is bounded by those two other functions. It is bounded by 1 minus x squared over 6, and it's bounded by 1. So here in this graph, we have represented in blue the function h of x equals 1. In red, we have sine of x over x, and in green, we have 1 minus x squared over 6. So this should look familiar to you. We have a complicated function for which we want to evaluate a limit, and it's bounded by two other functions, so we should use the sandwich theorem. But first, to use the sandwich theorem, we need the limits of the functions on the extremes of the inequality. So the limit of those two functions as x goes to 0 to be equal. So let's see. So limit as x goes to 0 of 1 minus x squared over 6. Well, simply plugging x equals 0 in this expression is going to give me 1 minus 0. So this limit is equal to 1. And the limit as x goes to 0 of 1 is simply equal to 1. So the limits of the functions in the extremes of the inequality, they are equal. So the conclusion is by the sandwich theorem. So this implies by the sandwich theorem, shorthand for a theorem, that the limit as x goes to 0 of sine of x over x is equal to 1 as well. And here we have the same information repeated, but typed. So to show that the limit of cosine of x minus 1 over x as x goes to 0 is equal to 0, we are going to use a trick that is similar to rationalization. Rationalization is just another expression for multiplying by the conjugate. So we are going to multiply both the numerator and the denominator of this function by cosine of x plus 1. So let's see, limit so multiplying by the same number in the numerator and denominator does not change the function. So this is going to be equal to limit as x goes to 0. So the numerator, if we multiply those two, is going to give us cosine square of x minus 1. And then in the denominator, we're going to leave as x times cosine of x plus 1. Well, now we are going to use one of the trigonometric identities. Remember that sine square of x plus cosine square of x is equal to 1. So cosine square of x minus 1 is going to be equal to minus sine of x, minus sine square of x, sorry. So it's going to be minus sine square of x over x times cosine x plus 1. Well, I'm going to rewrite this function the following way. I'm going to rewrite as minus sine of x over x times sine of x over cosine of x plus 1. Well, we just saw the special trigonometric limit, that the limit of sine of x over x as x goes to 0, that is equal to 1. So it means that the limit of this first term is equal to -1. And then let's see what happens with the second term. So as x goes to 0, sine of x goes to 0. So as x goes to 0, sine of x goes to 0. And let's see what happens with the denominator. Cosine of 0 is 1, plus 1 is going to be 2. So as x goes to 0, cosine of x plus 1 goes to 2. So this fraction here, it's going to 0 over 2, which is 0. So we have the first fraction going to -1 and the second fraction going to 0. So the conclusion is that the limit as x goes to 0 of this function that we have, which is equivalent to the first function, which is cosine of x minus 1 over x, it is equal to 0. And here we have the same information but typed. So to summarize, we have the derivative of sine being equal to cosine of x and the derivative of cosine being minus sine of x. This is what we're going to see next. And we're going to use those special trigonometric limits to determine the derivatives of sine and cosine. So here's the justification for the fact that the derivative of sine of x is equal to cosine of x. So we are going to use the limit definition of the derivative. So that's limit as h goes to 0 of sine of x plus h minus sine of x over h. Now we are going to use a trigonometric identity to substitute sine of x plus h. So this is limit as h goes to 0. So sine of x plus h is going to be sine of x cosine of h plus sine of h cosine of x. And then we repeat the minus sign of x, and that over h. Well, in the first term, we have sine of x, and in the last term, we also have sine of x. So I'm going to factor that sine of x. And then I'm left with cosine of h from the first term. And from this term, we have -1. So cosine of h minus 1. And then we cannot forget that we have another term, which is sine of h cosine of x. And all of that over h. And now I'm going to rewrite this the following way. So this is the limit as h goes to 0 of sine of x times cosine of h minus 1 over h plus cosine of x times sine of h, that over h as well. Oops. Well, we just saw the special trigonometric limits, and we saw that this limit, so the limit of cosine of h minus 1 over h as h goes to 0, this is going to be 0. And we also saw another special trigonometric limit that says that limit of sine of h over h as h goes to 0 is equal to 1. So this is equal to 1. This is equal to 0. And the fact that we have a 0 here is going to make the first term equal to 0. So this limit is simply going to be equal to 1 times cosine of x. So that is equal to cosine of x. So we began with the limits definition to prove that to find out what the derivative of sine of x was equal to. And the conclusion was that this limit was equal to cosine of x. So the derivative of sine of x is equal to cosine of x. So I do not have the proof in the slides for the derivative of cosine of x, but it's very similar. You're going to apply the limit definition and you're going to conclude that it's equal to minus sine of x. And if you write it down and send it to me by mail by Monday, January 25th, I'm going to give you a participation point if your proof is correct for the derivative of cosine of x. So let's see one example. We have to find the derivative of this function, minus cosine of x times minus cosine of x plus 17 over 3 times sine of x. We are going to use all the information that we have about derivatives so far. So f prime of x is going to be the derivative of the first term. But instead of writing minus cosine of x, I'm going to write cosine of x. And I'm going to put the minus sign in front. And I'm doing this because we have a property that we saw in a previous video that tells me that if I multiply a function by a constant, by a real number, it's the same thing as taking the real number, taking the derivative of the function and multiplying by the real number. So that's what we are doing. That's the constant rule. So we are going to do the same thing for the second term, 17 over 3 times the derivative of sine of x. Well, we just saw that the derivative of cosine of x is minus sine of x. So we have a minus in front, and then derivative of cosine is minus sine of x. The 17 over 3, we repeat. And then the derivative of sine of x is equal to cosine of x. So this tells me that the derivative of that function is equal to sine of x plus 17 over 3 cosine of x. And here is the same information, but typed. Now let's take a look at a second example. Let's find the equation of the tangent line to the graph of this function at the point pi over 6 square root of 3. So if we have to find the equation of the tangent line, we are going to need the slope and the point. The point is given. The point is given. So we need to find the slope. And to find the slope, we need to find f prime of pi over 6. That is going to be equal to our slope, which I'm going to call mt. So the slope of the tangent line. So let's find first the derivative of the function. So we have a constant, and the function f is a constant 2, and a trigonometric function cosine of x, which we just saw that the derivative of cosine of x is minus sine of x. So we keep the 2, and then the derivative of cosine is minus sine, so the derivative is going to be minus 2 sine of x. Well, if we want to find f prime of pi over 6, we simply plug pi over 6. So this is going to be minus 2 times sine of pi over 6. So minus 2. The sine of pi over 6 is equal to half. So f prime of pi over 6 is equal to minus 1. Well, to give the equation of any line, it's given by y minus y0 equals m times x minus x0, where m is the slope and x0, y0 is the point. So the point was given to us pi over 6 square root of 3, and the slope is going to be the slope of the tangent line, which we just found that is equal to -1. So we're going to have y minus square root of 3 equals -1 times x minus x0. X0 is pi over 6. You can leave like that. This is called the point slope form of the equation of a line, or you can solve for y, and that's going to give you an equivalent answer. Here we have all the information again, but typed. Let's take a look at one more example where we have to find the limit of sine of 7x over 4x as x goes to 0. So in this case, we are going to need the special trigonometric limit that we saw in the beginning of the video. So the trick here is the following. We saw that limit of sine of x over x, over x as x goes to 0, that is equal to 1. So here we have x, but we could have anything else, like it could be sine of, let's see, sine of y over y, and then this would be equal to 1. It could be limit of sine of 7x over 7x as 7x goes to 0. This would be equal to 1. Well, my point is we need to have the same thing in the argument of sine and in the denominator. So we have a sine of 7x. We should make a 7x appear in this expression. So we have limit as x goes to 0 of sine of 7x over 4x. What I'm going to do is I'm going to multiply both the numerator and denominator of this function by 7x. And this is going to be equal to limit as x goes to 0 of sine of 7x over 7x times 7x over 4x. I just rewrote, I put this numerator with this denominator, and then this numerator with this denominator. Well, because we have in the second fraction, we have x in the numerator and x in the denominator, they cancel each other. And now as x goes to 0, 7x is also going to go to 0. So we can use our special trigonometric limit that tells me that this limit is equal to 1. So the limit of the first fraction is 1. And for the second fraction, we have simply 7 over 4. So this limit is going to be equal to 7 over 4. Let's take a look at one more example to use the special trigonometric limit. So limit as x goes to 0 of x times cotangent of x. I'm going to replace cotangent of x by cosine of x over sine of x, because cotangent is the inverse of tangent. And this is equal to limit as x goes to 0 of cosine of x over sine of x over x. So the x that I had here in the numerator, I put it here in this denominator. And why did I do that? This is a trick that makes this limit work. So I did not expect you to know this trick, but now that I'm telling you, you can use this trick. So as x goes to 0, cosine of x goes to 1. And then for the denominator, where we have sine of x over x, as x goes to 0, we can say that this denominator is going to 1 using our special trigonometric limit. So this is simply going to be equal to 1 over 1, because the numerator goes to 1 and the denominator goes to 1 by the special trigonometric limit. So the final answer is equal to 1. Now, we are going to use the derivatives of sine and cosine to evaluate the derivatives of tangent, secant, cotangent, and cosecant, because they are defined as ratios involving sine and cosine. And we have already seen how to evaluate the derivative of quotients, derivative of fractions. So let's start with the derivative of tangent of x. Well, tangent of x is equal to sine of x over cosine of x. We also know that derivative of sine of x is equal to cosine of x, and the derivative of cosine of x is equal to minus sine of x. So we are going to apply the quotient rule to obtain the derivative of tangent of x. So you can remember that trick that I told in a previous video. So derivative of a fraction is low d high minus high d low over low square. So we're gonna have low times d high. So derivative of the numerator, derivative of sine is cosine. So we have cosine of x times cosine of x minus high d low. So high is sine of x and d low. So we are going to take the derivative of cosine of x, which is minus sine of x. So the minus is going to become positive with the minus sign that we already had in front. So sine of x over the square of the denominator. So cosine square of x. Well, this numerator is equal to cosine square of x plus sine square of x. So we are going to use a trigonometric identity here. So sine square of x plus cosine square of x, that is equal to 1. That's one of the reasons why trigonometric identities are so important. So we have 1 over cosine square of x, and that by definition is equal to secant squared of x. So we found the derivative of tangent is equal to secant square of x. And that's what we have in this slide. Next, we are going to evaluate the derivative of secant of x. So it's going to be the derivative of, I'm going to write secant of x as 1 over cosine of x. And I'm going to apply the quotient rule. So it's going to be low d high. So cosine of x, derivative of the numerator is a constant, so derivative of constants are 0, minus high d low, so minus 1 times the derivative of the denominator. Derivative of the denominator is minus sine of x over the square of the denominator, so cosine squared of x. Well, this first term in the numerator is going to be 0, and the second term in the numerator is going to be sine of x. And then we repeat the denominator. I'm going to rewrite this as sine of x over cosine of x times 1 over cosine of x. So sine over cosine is equal to tangent, and 1 over cosine is equal to secant. So the conclusion is the derivative of secant is tangent times secant. And that's exactly what we have in this slide. Now let's evaluate the derivative of cotangent of x. So cotangent is 1 over tangent, and since tangent is sine over cosine, cotangent is going to be cosine of x over sine of x. So once again, we're going to apply the quotient rule. That tells me by our mnemonic trick, it's low d high, so derivative of cosine is minus sine, minus high d low, so minus cosine, derivative of sine is cosine, over the square of the denominator. So this is equal to minus sine square of x minus cosine square of x, that over sine square of x. So sine square of x plus cosine square of x is equal to 1. So minus sine square of x minus cosine square of x is going to be equal to minus 1 over sine square of x. So this is equal to minus cosecant squared of x. So the derivative of cotangent of x is minus cosecant squared of x, which is exactly what we have in this slide. And finally, let's evaluate the derivative of cosecant of x. So remember that cosecant is 1 over sine. So once again, we're going to apply the quotient rule. So low d high. So the derivative of the numerator is 0 minus high d low. The derivative of the denominator is cosine of x over the square of the denominator. So the first term in the numerator is going to be 0. The second term is going to be minus cosine of x. And then we have a sine square of x here. So I'm going to rewrite this as minus cosine of x over sine of x times 1 over sine of x. Cosine over sine is equal to cotangent. So this is going to be minus cotangent of x times 1 over sine is equal to cosecant. So the derivative of cosecant of x is equal to minus cotangent of x times cosecant of x, which is exactly what we have in this slide, but typed. So now we know the derivatives of the trigonometric functions, and we have a summary of them. So let's use the knowledge that we have to find the answer to this example. For which values of x does the graph of f of x equals e to the x times secant of x have a horizontal tangent? So horizontal tangent means that the slope of the tangent line is going to be equal to 0. So it means that we have to set f prime of x equal to 0. and then find the values of x that make f prime of x equal to 0. That's what the question is asking. So let's evaluate the derivative of f. Because we have a product here, we are going to apply the product rule. So this is the first term, this is the second term. And to evaluate the derivative, we are going to apply the product rule. So we are going to leave the first term as it is and multiply by the derivative of the second term. So derivative of secant is secant times tangent. And now we differentiate the first term, while derivative of e to the x is e to the x itself. And we leave the second term as it is. So secant of x. We have secant of x in the first term. We have secant of x in the second term. So I'm going to factor. And I'm left with e to the x. Well, we also have e to the x in the first term and in the second term. So actually, I'm going to factor e to the x times secant of x. And then I'm left with tangent plus 1. So we have to set f prime of x equal to 0. So this means that e to the x times secant of x times tangent of x plus 1 is equal to 0. So e to the x is never going to be equal to 0. Secant of x is never going to be equal to 0 either. So we have a product of two things that is going to be equal to 0. But this term is never going to be equal to 0. So it means that we need to have the second term being equal to 0. So tangent of x plus 1 has to be 0, which means tangent of x is equal to minus 1. So tangent of x being minus 1 means that x is equal to let's see, 3 pi over 4, and then plus pi times k, where k is any integer. And this was our last example for this video, and I'll see you next time.